Today we're going to take a look at how we can estimate the uncertainty behind the adjustments we make when we take some model or just a moving average or a kernel regression, something like that, and we want either to visualize how uncertain we are about the fit between our curves and the data, or we want to actually estimate the confidence interval or the uncertainty in the parameters we're trying to find if we have a model with parameters. So previously we saw how to select models, how to fit them, so measuring the error outside the training set to select the best models or select the best values for hyperparameters. Once we get this final hypothesis, this curve adjusted to our data, how do we have an idea of how well the fit is at different parts of our data, or how we can measure the uncertainty in the parameters that we find. So today we're going to see a general approach of bootstrapping, so basically resampling our data to obtain replicas and measure some statistics there, and then a specific variant wild bootstrap for some particular cases like time series. But I'll start with an example for illustrating bootstrapping. So from this survey from the United States of the National Health and Nutrition Examination Survey, I extracted some data on weight, height, and sex of a subset of participants. So this is the data file that we have. We have the weight here in kilograms, the height in centimeters, and then a flag, a label indicating whether the participant is female with value 2 or male with value 1 there. This includes participants of all ages, so we have children, adults, old people, etc. And we can plot the relation between height and weight for all these participants. One thing that is useful to do if you're going to do plots for reports, for your thesis, things like that, is write auxiliary functions that help you fine-tune how you want the plots to appear, and this then makes it easy to standardize your plots, to make them all look the same and have the same kind of graphic design and things like that, colors and so on. So what I show here to illustrate this is I create an auxiliary function just to plot this data into two different classes, male and female. So it's two subsets of participants represented with different colors. And this way we can specify how to plot the data, what will be the interval of interest in the x-axis. So I'm going to use the weight for the x-axis and focus on weights between 10 and 100 kilograms. So I selected a part of the data without outliers, without very young people, babies and so on, and without very heavy people. And this will be a useful function every time I want to superimpose the data on some other plot, some trend line or things like that. So to do this, I don't include the creation of the actual figure inside this function, so that I can use it to superimpose the data on any plot I want. But then I add here some things that I can decide previously: what will be the limits of the axis, what will be the labels, the colors that I'll use to represent each class in our data, and things like that. So this is a useful approach if you need to do several plots. Write auxiliary functions where you fine-tune these options, and then you just use the function like this. So I load the data, I separate male and female participants based on the label on the last column. This is something we saw in the beginning, using these Boolean arrays to index the rows on our matrix. And then I just create a figure and call this auxiliary function that I can fine-tune and adjust to my taste until I get the plot the way I want it. So this is how the data looks like. And in general, when you're doing any kind of data analysis, it's always a good idea to start by looking at the data and get a more intuitive feeling of what the shape is, how things look like. And we can see here represented in red the female participants and in blue the male participants. Now we can superimpose here on the data a trend line that we can create using kernel regression. So this is what we saw in the previous session, but just a quick recap. For kernel regression, we use a kernel function that allows us to weigh points in the neighborhood of the point we're trying to predict by using this function that will usually decrease along the distance and needs to have those properties of having an area of 1 being greater or equal to 0 everywhere and symmetrical. So in this case, I'm using a Gaussian kernel. This is the Gaussian curve that I use to weigh differently points as they are further away from the point I'm predicting. And then we need an estimator that takes this weighted average and aggregates it in some way. So this estimator that we saw previously is basically just a simple weighted average where we use the values from the kernel to weigh the different points, and we divide everything by the sum of the weights. So with this kernel regression, we can look at the trend between the trend of these two series of data by again creating a simple auxiliary function that we provide the data, the values along the x-axis where we want to draw the trend. So we're going to compute the kernel regression for these values, and the color with which we want to represent our trend. Then there is this additional parameter here, the width that we apply to the kernel, that makes the kernel effectively wider or narrower, so focusing more on points that are further apart and smoothing more the trend, or focusing more on points in the near neighborhood, which makes the line twist and bend more. So I just use the default value of 3 here. So remember that since this refers to the x-axis, this is a width of about 3 kilograms for the smoothing factor along this the weight axis. So now we create a figure, we plot the data, and then we plot the trends for male and female participants using this set of values for x. So between 10 and 100 kilograms, I create 100 points, and then I join them with these lines. So the blue line here is the kernel regression for the male participants, you can see here, and the red line is the same for female participants. Now, when we look at these regressions, we can see some things like a difference here when for adults and people with more age, weight and height, we can see a difference between male and female participants in the relation between height and weight. But we can also see these curves here. For example, it seems that in children, it looks like girls start becoming taller for the same weight than boys, but then when they grow a bit older, boys become taller, and then they seem to be again at the same height for the same weight, and so on. So the question is, we are looking at this difference in the trend, but the question is whether or not these are actually differences in the data, or if they are just basically noise. It happens because we just got this particular sample, and in this particular sample we have this distribution. So one thing that we can think is that if these differences are real, then if we could repeat the measurement with a new set of participants, we would get approximately the same results. Or if we would repeat this, say 1,000 times with different sets of participants, we would tend towards having the same kind of results. If not, if this is just something that happened to occur in the particular sample that we got, then results would vary as we would repeat the experiment. The thing is that it's not practical now to do this 1,000 times with different sets of participants, because gathering the data is expensive and time consuming, and we only have these data to work with. But we can do something that is analogous to repeating the experiment. Let's think of our data as a representative sample of all possible subjects. So we don't have all possible subjects, we only have this sample, but this sample we can assume is approximately distributed in the same way as the actual universe of subjects is distributed. So we could fake a new set of data by, instead of resampling the actual universe of subjects or gathering more volunteers to participate in the study and measuring all these attributes, we could get that by resampling from our data as if our data was the actual universe of possible subjects. So this is the idea of bootstrapping. And in this particular case, we can do it like this. We can create replicas of our data in each replica by generating the same number of points that we have in our data, this n number of points depending on the size of our data, and each one is picked at random from the original data. So since we are just picking at random, sometimes we're going to pick the same example that we already picked before. So on average, 1/3 of the replica will be composed of repeated examples that are already in the replica, because we are doing this at random and we are not making sure that we have no repetitions. Because some of them are repeated in the replica, some points will be missing because the replica will have the same number of points as the original data. So this means that all replicas will be different because we have different combinations of the original point in different numbers of repetitions of some of them and some points missing from the replica. So we can think of each replica as if it was a different experiment where we collected statistics from a new sample of people, but instead of having to do the actual experiment, we just resample from the data that we have. And now we can run our, we can fit our models or run whatever we were running with a single data set. We can do that for all the replicas and then collect the statistics from those replicas and estimate the uncertainty. So let's see how we can do this with these kernel regression trends for the height and weight data. Let's create this auxiliary function to help do the bootstrap on the regression. And for this, we receive the data that we have, the number of replicas that we want to do, and the values on the x-axis where we are going to compute the regression. So remember that we have a set of data, but we want to draw a line along a set of points. So we give these x values where the regression will be computed, and this is the width of the kernel that we're going to use. So the way this function works is that it will loop through all the replicas that we want. So let's say that we want 5 replicas in this case. So we have here, we give a number 5 to this argument. So we're going to loop here 5 times. By the way, this underscore here, I'm not sure if you covered this in your Python course, but if you're using a variable that you need to use for syntactic reasons for because of the language, so in this case we need a variable in these iterations, but if you don't care about what the variable is, we don't really need to know which replica we are dealing with, the actual number, you can use the underscore so you don't get warnings about variables that are not used and things like that. So this is just to repeat the code the number of times specified in this replicas argument. And what we do here is we generate a random an array of random integers. We can do that by using the random module from NumPy, and we have this randint function that we can specify the lower bound, the upper bound for the random integers, and how many we want in the array. So in this case, since we want indexes for the rows in our data, we want them to go from 0 all the way to the number of rows in our data. So actually this doesn't go exactly to that number. It's always 1 below the upper bound we put here. So this allows us to generate indexes at random for the rows in our data, and we want as many of these values, of these random values, as we have rows in our data. But note that since these values are chosen at random, we may be missing some rows and having other rows repeated because we are not making sure there are no repetitions. So this is not a permutation of our data like we did when shuffling the data, for example. This is actually a set of random numbers that can have repetitions. So now the replicated data is simply from our data the rows that we got at random here and all the corresponding columns. So this will be each replica. And now we can append to our lines the result of doing the kernel regression that we did with the specified kernel width for that particular set of x values and using the replica as the reference data. Okay, so now we can create a figure, define the range where we want to draw the trend line, so between 10 and 100 and 100 points evenly spaced. And we're going to do this for the female participant. So we're going to plot the female data and compute these lines for these participants and plot all 5 lines. So this argument here tells the function how many replicas we want. We want 5. This will return an array with all the different lines obtained in the different replicas. And this is how things look like. So if we draw 5 lines by creating different replicas from this dataset, you can see 5 examples here. They are different because each line was created from a random subset of these points with some repetitions, and this created this variation that we see in the lines. So this is the idea that we can now use to provide us with some range of confidence where we think the actual trend may be. So let's improve this. We're going to use the percentile function from NumPy, which can give us the percentiles from an array of values. It can be a matrix, for example. So in this case, what we're going to do is we're going to compute this bootstrap regression. We're going to use this function here, but we're going by default to ask for 1000 lines. So using 1000 replicas. This gives us a reasonable sample. It takes a few seconds to run, but it's okay. It's not much time. And now we have 1000 trend lines created with the kernel regression using 1000 replicas by bootstrapping from our data. So this will be the matrix with all these lines. Each line is a row, and we have 1000 rows with all the different lines that look somewhat like this. And now we can use the percentile function to get the median of this. We can actually use the median function for this, but I just use the percentile for the same things to illustrate how this percentile function works. So by giving this matrix that has 1000 rows, and on each row it has one of these lines, the y values for these lines, we can ask for the percentile 50. So this is the median of these values, and if I specify the x is 0 in a matrix is in the direction of the rows, this means that the percentile will be computed by projecting along the rows. So the first value will be the median of the first column by running through all the rows, the second value the median of the second column, and so on. So since this is just a scalar value, the percentile function returns a vector with all the medians computed along this axis for this matrix. I also want, besides representing the median here as a line, I also want to show the confidence interval. So I'm going to pick 99% and 90% confidence interval. So this means that for the 99%, I'm going to go from 0.5% to 99.5%. So everything in between will cover 99% of the lines. And for the 90% interval, I'm going to go from 5 to 95. I can do this in one go by calling the percentile function and giving an array, in this case a list, with all the percentiles I want. If I do this, then the function will return a matrix with each of these percentiles in a different row. So I could actually have included this 50 there by any order that I wanted, and I could have used it like this, but I just did this in two parts to show you different ways you can use the percentile function, because this is useful for many other applications, not just this example. And now I will draw the line at this regression line would be at the median of all the lines I obtained, and then I'll use this fill between function of pyplot to fill between the first and the last percentile here, so 0.5 and 99.5%, a bit more transparent, and then fill between the two in the middle, so between 5 and 95 percentiles for the 90% confidence interval. So with this function, now I can just create a figure, define this x set of values for drawing the lines, and now I can plot this confidence interval along the graph for the female participants. So this is what I get as an example. So you can see here the darker shade of red is corresponds to the interval of 90% confidence, and then 99% we see a lighter shade of red, and in the middle we see the trend line in the corresponding to the median of all these lines. So this way we have some information also about how not only what the trend is, but how uncertain we are in different places. For example, look here that despite there being quite a good dispersion of data points, since we have many data points, all the lines tend to pass in a very narrow band here. In this part we have fewer data points, so we have more uncertainty about where the actual trend will go. And now we can use this to compare the two. So we create a figure, we plot the male and female data, and we plot using bootstrapping both sets of participants, and we have this result. So this gives us a better idea of what the actual trends are, rather than just looking at the lines, because the lines by themselves do not give us any information about how uncertain we are at each place in the graph. And here we can see that these crosses here, where one was over the other and vice versa and so on, they don't seem to be very significant, because the confidence interval here is quite broad relative to that distance. So basically this may just be an artifact of our data, and we cannot say much about what happens in children when they're growing. It seems to be more or less the same kind of relation, whether it's boys or girls. It's only after about 55 kilograms of weight and so on that we can start seeing a significant difference between men and women at this stage. So this is something that you can use. This is not really quantitative in the sense that we are not yet using for estimating any parameters or confidence intervals for parameters, but even just in visualization for looking at the data, it's always useful to have an idea of how uncertain you are. So this gives a lot more information than just fitting the curve and using just a single line for your fit. Okay, so another thing that we can do, in this case with the kernel regression, we don't have a parametric model. We are not computing any specific parameters. We are using the data itself to compute those weighted averages and get these trend lines. But we can also use bootstrapping when we want to fit some parametric models, also to determine uncertainty about the parameters. So let's look at an example here. There is this book by Gabriel Tarde from the late 19th century. It's about how ideas are adopted, and this also applies to economics and finance and things like that. So basically, he proposed that there were three stages. There was an early stage where there was some opposition to the idea, because a new idea had to compete with established practices and so on. And then people start adopting the new idea. They see that it's a good idea, so there's exponential growth. But eventually we can have some sort of saturation or competition for even more recent ideas and so on, and the growth will slow down. And this can be modeled by a logistic function. I'm going to show you the model in a bit. But first, I'm going to use this data from biomass use in USA from the second half of the 20th century, so 1949 to 1999, to produce energy. And this is in trillions of British thermal units, the units I'm going to use. But we have the data here in this file. The first column is the year, the second column is the energy produced using biomass, and we can just take a look at the data. So this is a time series. We have 1 point for every year, and for each year we have here how many trillions of BTU were produced using biomass for energy production. So you can see that there was this initial stage where nothing much was happening, and then suddenly production of energy using biomass grew a lot, and then there are these oscillations here at the end. So we're going to try to fit this with a logistic function following this model by Gabriel Tard, and the logistic function looks like this. We have this L parameter here, and then we divide by 1 plus e raised to minus k. X is the input value here, and this is another parameter, x0. So basically what these parameters do is that L determines how high the curve will be, so the difference between this low point and the high point. If we have L equal 1, we have a curve like this. With L equals 2, we have a curve like this. The k parameter here will determine the slope of the curve. So if k is higher, the curve has a steeper slope. If k is lower, then the curve has a more gentle slope. X0 determines where is the midpoint on the x-axis for the curve. So if we have an x0 of -1, the midpoint will be here. If we have an x0 of 1, the midpoint will be here. So by changing these parameters, we can change the shape of the curves, how high it is, how steep it is, where it's adjusted on the x-axis. And now we just need a small modification, because if you see, our data does not start at 0. People were already using biomass to produce heat and energy and so on before growth started here. So we need to add some constant value to our function to be able to adjust this. So we're going to modify this slightly by adding this offset value here that we can use to shift the curve higher or lower as necessary. So basically we have this model with 4 parameters, L, K, X0 and the offset, that we can now use to try to fit our data, the data that we have here. We already saw how to do this. So we use the minimize function from SciPy optimize, and we create a loss or cost function or a loss function that we're going to minimize to adjust the parameters. So in this case, this is just the logistic function here. So L over 1 plus e raised to minus k x minus x0. This is just the transcription of this function here to Python. And then for the cost function, we receive the set of 4 parameters. We can unpack that into these variables so we don't make mistakes by indexing the tuple there. And the prediction will be the result of the logistic function using the x values on our data and these 3 parameters, x0, l, k. But then we add the 4th parameter, so we get this modified version here, so that we can adjust the curve higher or lower. And now we compare that prediction with the actual data, and this is the mean quadratic error between what we are predicting with the curve and what the data is. So now this is what we're going to minimize with the minimize function. So we're going to minimize this cost function here. It's a good idea to give a generally approximate set of parameters, because if we don't do that, it may take a while to minimize, or it may fail to find a combination of parameters. This is especially true if you have many parameters. So, but we can just eyeball it a bit. This is x0 is where the curve, the midpoint here, so we can see that it's maybe about 1980 or around 1980 should be the x0 value. Then we have this parameter L. It's the difference between the low and upper value. So this is about 1500 trillion BTUs. This is the offset. It's the origin here, so it's around 1500 also. And then we can just put a small value for the K. I have no idea just by looking what the K parameter would be, but we start with a small value and let the algorithm minimize. So usually if you don't start with very approximate values, it's okay, but if you can just take a look at the graph and see what you would expect, you can just input those parameters as the starting point, and the closer you are to the actual value it's going to find, the better things will run. So now we run the minimization, we get the result here in this X field on the result of the minimization. We unpack these parameters here, and now we compute the prediction. So I call the logistic function with the parameters that were computed by the minimization. I add the offset, and this is my prediction that I plot here, and I also plot the data as a dot. So this way we can visually compare the fit of our model, so what our model is predicting after fitting, with the data, and see if things make sense. So it seems to fit rather nicely with the data, and we have this good looking logistic curve here. Now the question is, what can we say about these parameters? We can plot the parameters. So this is x0 is the midpoint, 1978.8. So by late 1978, apparently from our model, was where we were halfway between these two changes. This is how much things change. 1591 was the difference between what was before and after this change in production of energy from biomass, and the start and so on. But the thing is, what's actually the uncertainty about these parameters? Can we say that this is exactly 1591, or is there some margin here because these points oscillate quite a bit? So this is one thing that we can try to quantify with bootstrapping, understand what are the confidence intervals for our parameters. One problem with applying just the basic bootstrapping algorithm here is that it doesn't make sense to pick years at random. So we cannot create replicas of these data just by choosing at random which years we're going to use, because we are actually measuring every year. If we were to repeat the experiment, we would have measures also every year, because that's the whole point of doing these yearly measures. So we need to do something different to get replicas of our data and try to approximate what would happen if we were to go back in time and repeat all these measurements along the time. So one solution for this is called wild bootstrap, and this starts with the assumption that the model we fitted is predicting the value, but there is some noise, there is some random noise that we get, and also this noise can change from year to year. So you can actually see that here. There seems to be a very low variation here at the beginning, and then much higher variation here at the end. So we cannot just assume that the standard deviation for the noise on these years would be the same as for these years. So this wild bootstrap allows us to use different variances of the noise along our data. So we can say that we can try to predict some true value or some new value for the replica, something that would occur in a new experiment with the value we actually predicted after fitting our model, plus some normal distributed noise with different standard deviations for different points that we have, so that we can capture this idea, this intuitive notion here, that these points are deviating less from the curve than these ones here. But we need to pick a value for these standard deviations, and for that we can use the residuals. The residuals are the differences between what our curve is predicting and the actual data. So the data minus the curve gives us these red lines here, and these are the residuals for each point that we have. So we can see that some points are very close to the curve, others are further apart from the curve, and the residuals are different from point to point. So this is how we can do wild bootstrap. We compute the residuals, and each residual is the difference between the value that we have in our data and the value that we predicted from our adjusted model. And now we can assume that we have some dice, some random variable that we can generate that is normally distributed, and we're going to create a new replica for each point by adding to our prediction the residual that we have for that point multiplied by this random variable normally distributed. So it has a mean of 0 and a standard deviation of 1. This means that points that that have higher residuals would generate replicas that can be farther away from the prediction than points that have smaller residuals. Okay, so here's the implementation to do wild bootstrap with this logistic function that we're trying to fit. We're going to create a matrix for the replicas that is just a copy of our data. So we have the same size and the same values of x, because when we compute the actual curves, we need to provide the whole data to the cost function. So we're going to create a new matrix to store the replicas. But now the y values for the replicas will be the prediction plus the residuals multiplied by these normal random numbers. So basically I'm using from the random module the normal distribution, and the size argument specifies how many normally distributed random numbers I want. So I'm getting a vector with the same number of elements as the number of rows I have in my data, and this is what I'm multiplying by the residuals element by element and adding to the predictions. Now the prediction is the original prediction I have from this curve here. So these are my predictions for each point, the first curve that I got by fitting the model. So what I do is I fit the model by minimizing the log cost function there with the starting parameters that can be specified here, and I unpack the results here and I create the prediction. This is basically the same thing we did here to plot this graph. So doing the minimization and computing the prediction is the same thing we did to plot this curve. So this is the actual curve that we're going to use as the base prediction. And now the residuals are the differences between the data and the corresponding predictions. So all these red lines here are the residuals that we have from this prediction. And these are the ones we're going to use to generate the replicas. Now for each replica, we're going to compute a new curve. We're going to get the parameters and we're going to compute the prediction here. So this computes the parameters by the minimization. We store the vector of parameters there in this array, in this list of parameters, and then we compute the prediction for these particular parameters and we append that to these lines here. So we return two matrices at the end. One is a matrix that has 4 columns for these 4 parameters here, and 1 row for each replica that we computed. So this tells us what the parameter values were for each replica. And this is similar to what we did before. We get a set of lines with all the predicted values for the different fits using the different replicas of our data. Now, if we want to see the confidence intervals for those lines, so visualize the uncertainty there, I write a function that is very similar to the one we saw before. So in this case, I already received the lines. So I compute the median here using the percentile 50. And then I compute these confidence intervals for all these lines and do the plot like before. So basically, the 90% confidence interval I draw with a darker color here. And the 99% confidence interval I draw here with a lighter color. Now, putting all of this together, we create a new figure. We do the bootstrap of the logistic fit using our data, those initial parameters that we already saw just approximately by looking at the plot, and 1000 replicas. And now we plot the data and the bootstrap lines like this. So this is the result here. We can see that there is lower uncertainty here at the beginning than at the end, because we have a greater variation of values here. So this intuitively makes sense. And here in the middle, there seems to be the range here is very narrow. So doing replicas here doesn't change very much the midpoint there. And we can actually see these in the parameters that we computed. So in this case, I can just print out the different values. So I skip this a bit here on this other slide. I'm not sure if how much you know about these formatting strings, but I'll explain this now at the end. By prefixing a string in Python with f, at least in Python 3, you can include in curly brackets expressions that the interpreter will evaluate to give before inserting in the string. So in this case, in brackets, I put x0, and it will show me the value of x0. These codes afterwards, you can check the documentation, but this is basically to determine how the numbers will be converted to strings and how they will be represented. So this is this f here indicates it's a floating point number, and 0.1 means I want one place after the decimal point here. So this will have one place. This one has 0.3f, so this will have 3 decimal places, 3 places after that decimal point there. And so this is the notation. You have the numerical expression, and then you indicate how you want it formatted. So here, what I did is I take the median of the parameters. So this is the 50% percentile for all the parameters, and I unpack this to these 4 parameters. Remember that these parameters matrix is just the list of all the parameters obtained after looping through all the replicas. So in this case, it has 1000 sets of parameters, and this was converted into a NumPy matrix at the end. So it's a matrix with 4 columns for the 4 parameters and 1000 rows for all the different replicas. So if I take the median here on the axis 0 along the rows, I take the median of each column, and so this x0, l, k, and offset will be the median values for each of these parameters. And I can do the same thing with the matrix, but for computing the standard deviation. So now I have the standard deviation for x0, l, k, and so on. And I can then represent this with a plus minus the standard deviation. So we can see that this 1978 value, or at the end of 1978, is really very precise. There is no great variation there along the replicas. So if we do wild bootstrap with our data, we always get approximately the same value. So near 1979 at the end of 1978. For the change, so this variation between before and after the adoption of or the more widespread adoption of biomass for producing energy, we see that there is about 30 standard deviations. So if we were to consider, for example, 2 standard deviations, something like that, we'll have about 60 or 70 in range either side of this 1593 value. And a similar thing for the start, but we can see that the starting point here has a lower variation than the end. So this standard deviation here is different. So this is one thing we can do with bootstrapping, get an estimate of how what are the confidence intervals for our parameters, and we also can visualize. So you can do the histogram, for example, of the L values, the difference between the beginning and the end of this curve by plotting the histogram of the second column of our parameters. So just follow the order here x0, L is the second column, so it's the column of index 1, and we can use the hist function from pyplot just to look at the distribution of values. And we can do the same thing for other parameters. For example, this is for the offset, and so on. So, to sum up, we can use replicas to estimate or visualize or quantify the uncertainty we have in our fits. So if you're doing things like moving averages or kernel regression or something like that, just to help understand the data, we are not actually trying to predict anything, but you can still use bootstrapping or a variant of bootstrapping to produce these intervals where you have an idea of how uncertain that that trend you're computing is. But you can also use bootstrapping to estimate and quantify the intervals of confidence of parameters when you have actually parametric models that you're fitting to your data. And some of these parameters can have the most useful ones have actually some meaning, and this can help you understand better the data. The difference between bootstrapping in general, like we saw at first, and in particular wild bootstrap, is basically the general idea of bootstrapping is obtaining replicas from our data, and the default is just to resample at random from the data. This is good when all the values in the data are actually randomly sampled from the universe we are studying. So, for example, the height and weight of people who participate in those studies have been sampled from the population in general at random. So if we resample from the data, we get something that is approximately distributed in the same way as the original data that we have. So bootstrapping is good for those occasions. However, it's often the case that part of the data that you're using is not actually random. For example, the year at which each measurement was made, it's not picked at random because we are measuring every year. When you have these kind of situations, we can use the residuals to estimate how much variance we're going to put on each point. So in wild bootstrap, we do it like this. We assume that different points on our data have different distributions of error, and we use the residual at each point to estimate that. There are other variants. For example, residual bootstrapping just resamples the residual. It assumes that the distribution of residuals is the same over all the data, and so on. So you have, if you take a look, for example, you can start with Wikipedia, you can see very different variants of bootstrapping. But the important thing here is this general idea of resampling in some way to obtain replicas of the data in order to estimate uncertainty.